Fahrenheit prior to liftoff, electrical heating in orbit will not be necessary as previously thought. Additional research and development conducted during April, May, and June of this year has assisted the Mercury program, and continued endeavors in this segment of the project are progressing now. With 13 spacecraft out of the original 20 called for under the McDonnell contract, most of the major spacecraft construction has been completed. Modifications and equipment installations are progressing on schedule. Production spacecraft 15 has completed individual system testing. The necessary engineering changes in wiring of the antenna fairing separation sensor were being made, and the cabin interior was inspected. Recovery compartment equipment of number 16 was inspected, and the spacecraft was in the final stages of assembly. After being changed to a manned orbital flight mission, spacecraft 17's pressure suit transducer was installed. Reaction control system components were inspected, and the spacecraft entered the final steps of assembly. On Capsule 18, a bevel was ground on a bushing near the bulkhead ring for fitting of the exterior shingles. Also in final assembly is spacecraft number 19. The manual control mechanism was installed in the cabin interior. The last spacecraft under construction, number 20, nears completion. Recovery compartment components have been inspected and the diode package installed. Post-flight evaluations continue to be made on spacecraft number 6, used in the MA2 flight test. Crews working around the clock have replaced reaction control system components on spacecraft number 8, and a new insulation blanket was installed after the MA3 aborted flight. With the Mercury flight program entering its major launch phase, the delivery of spacecraft and the subsequent post-flight checks and inspections, plus data analysis of flight behavior, also has become the major portion of spacecraft manufacturing as of this date. The complexities of adapting primarily a military missile to the manned spaceflight program of Project Mercury have continued to harass the Atlas launch vehicle's reliability flight tests. During this period, major changes have been made in the fuel flow design and have greatly increased the vehicle's capabilities for use in the orbital missions of Project Mercury. An anti-vortexing plate was developed from analyzed data of previous Atlas launches, showing that liquid oxygen sloshing within the booster fuselage was causing momentary bending in the rocket body. The plate is attached to the baffle shelf after inspection. With the addition of the anti-vortexing plate inside the rocket body, fuel flows through these many holes, giving a more even distribution, preventing spasmodic engine firing during liftoff and staging. Attaching holes are aligned and drilled, and the plate and shelf are integrated, ready for inspection. The MA3 programmer was recovered from the in-flight abort more than 30 days later. It had withstood both the landing impact and the inadvertent running over by a heavy truck. With reinstallation of some minor electrical parts and readjustment to the wiring inside, the programmer underwent a series of tests. It was determined that the overall reliability and construction of the mechanism had successfully experienced the abort, the impact, and the accident remaining in working order except for the smashed transistors and wiring. The sustainer engine for production model 109D was installed and inspected. The engine was connected to the afterbody of the booster, and upon completion of installation and preliminary checks, the launch vehicle was raised high above the production line and moved to the dock where complete system checkouts were conducted. At Wallops Island, the construction of Little Joe 7's booster was progressing. The outer shell or casing was installed around the rocket's body, This single-stage, solid propellant test vehicle was constructed and test flown during this report period. 2 Redstone launch vehicles were delivered during April for use in the suborbital flight tests of Project Mercury. While data analysis and evaluation continue on the MA3 programmer, spacecraft and launch vehicle integration systems checks are being conducted to prevent recurrence of the malfunction in the MA4 Atlas booster. The 3 astronauts selected as a team for the first suborbital mission of the flight program were subjected to extensive tests during April, May, and June. Refamiliarization with the expected Redstone G loads and the accumulation of biomedical baseline data was carried out at the Human Centrifuge Trainer at Johnsville, Pennsylvania. Each of the 3 flew at least 2 Mercury Redstone G profiles. Special restraint and biomedical data gathering equipment from NASA's Ames Research Center was used during these training runs. In conjunction with the training factors, these tests furnish aeromedical data recorded for comparison with actual flight profiles for further evaluation. The astronauts were thoroughly checked by flight medical officers for any evidence of physical impairment that might result in their injury or disqualification in the scheduled flight tests. Other Redstone flight profiles were run and rerun using the procedures trainer at Langley Field. Simulated systems malfunctions and abort profiles were injected into the spacecraft trainer, and the astronauts here again practiced switching to the various manual controls backing up all of the spacecraft automatic systems. Roll, pitch, and yaw maneuvers were practiced using the manual control system's hand controller. Proficiency was gained in the use of this attitude control trainer. The 3-axis attitude simulations observed on this indicator familiarized the astronauts with flight roll, pitch, and yaw recognition. From 55 to 60 hours per week were spent by the astronauts in the procedures trainer number 2 at Cape Canaveral. Practice of the suborbital flight retro-firing sequence by the astronaut, the Mercury Control Center, and the Goddard computing facilities was conducted, although the Redstone missions will not achieve the speed for orbit where such firings will be necessary. Mercury control personnel underwent extensive training for the Redstone-boosted suborbital missions. This systems test allowed the Mercury Center, using the procedures trainer, to simulate actual flights for complete systems integration as well as operational training. Additional training was received by the astronauts as spacecraft communicators. Data was recorded in tapes made for use in tests of the tracking network for additional calibrations. With Project Mercury's flight program in its final qualification tests, the astronauts continue to practice in-flight coordination in high-performance aircraft and study aerial photographs and observation charts of both the Earth and the stars for visual recognition when in flight. Each Mercury flight is different, either in terms of the spacecraft, the launch vehicle, or the specific mission itself. And each astronaut continues to practice test runs on both static and stress devices to ensure that Project Mercury has the highest caliber test pilots with which to conduct its flight program. The ground tracking network, 18 stations in all, was completed during this quarter. Prior to the MA3 launch, the entire network was operational. The Bermuda station continued undergoing inter-systems checkouts. This facility is a duplicate control center with command control capabilities. The station was completed and ready for operation during the month of April. The final 2 stations to be completed were Kano, Nigeria, and Zanzibar. Simulated orbital flights using the procedures trainer at Cape Canaveral and test aircraft were plotted here at the Mercury Control Center.